Welcome. Today we're going to look at linear combinations and span. So let's get started with question 1, where we have u1 is the vector 1, 2, 3. u2 is the vector 2, 5, minus 1. u3 is the vector 4, minus 2, 3. And we are asked to write the vector v, 9 minus 3, 16, as a linear combination of u1, u2, u3. Okay, so to do that, what we seek are three scalars, alpha, beta, gamma, such that the vector v is alpha times the vector u1 plus beta times the vector u2 plus gamma times the vector u3. Right, because this here would be a linear combination of those three vectors u1, u2, u3, provided we can find the scalars alpha, beta, gamma such that this holds true. Okay, so let's translate this so that we can solve this problem. So alpha u1 plus beta u2 plus gamma u3 is alpha, 2 alpha, 3 alpha. So here we have alpha times u1, and then beta times u2, 2 beta, 5 beta, minus beta. Gamma plus u3, 4 gamma, minus 2 gamma, 3 gamma, equal to v, 9 minus 3, 16. Okay, now we're seeking to solve for alpha, beta, gamma. Now let's add the vectors on the left-hand side together. So we get alpha plus 2 beta plus 4 gamma, 2 alpha plus 5 beta minus 2 gamma, 3 alpha minus beta plus 3 gamma. So this vector is equal to the vector v, 9 minus 3, 16. Okay, so this is a vector equation, but matching the components, we can get three scalar equations right here. Okay, and so we want to solve this as a simultaneous system of three equations and three unknowns. Now let's translate this again to write a matrix equation so that we can perform Gaussian elimination. So here is our corresponding matrix equation. So next we can form the augmented matrix by concatenating the two of these so that we can solve for alpha, beta, gamma using Gaussian elimination. Now notice what this is. This is the concatenation of the four vectors u1, u2, u3, and v from left to right, which we can write just like this. Okay, and so our next job is to row reduce this, seeking the row reduced echelon form of this matrix right here, so that we can find alpha, beta, gamma, and hence write the vector v as a linear combination of u1, u2, and u3. So row reducing, the greatest common divisor of 2 and 3 is 6. So the goal here is to have the GCD of 2 and 3, or 2, 3, and 1 in my top pivot there on the left. And eventually I want to have zeros below that. So let's proceed to do that. So what I'm going to do first is multiply row 1 by 6, 12, 24, and 54. Let's multiply row 2 by 3. So we have 6, 15, minus 6, minus 9, and let's multiply row 3 by 2. So we have 6, minus 2, 6, and 32. Okay, continuing, now we have the opportunity to have zeros here because we have the same number there. So let's replace row 2 with row 2 minus row 1. So 6 minus 6 is 0, 15 minus 12 is 3, minus 6 minus 24 is minus 30, minus 9 minus 54 is minus 63. Okay, again, using our top row, let's replace row 3 with row 1 minus row 3, and I do it this way around so that I end up with a positive number here because I prefer that. So 6 minus 6 is 0, 12 minus 2 is 14, 24 minus 6 is 18, 54 minus 32 is 22, and now we can return row 1 to this version of row 1, which is to divide or multiply row 1 by 1 6. We have 1 6 row 1, 1, 2, 4, 9. Okay, so now we want the pivot to be where this 3 is, so we want zeros above and below that. So that's our second goal now that we've completed the first goal, which is to have an integer followed by 0. So to begin with, let's multiply row 1 by 3 so that we can have 6 here and here. And I can see that row 3 is divisible by 2 throughout, so we can also divide that by 2. So at least we get 7 down the bottom. Having multiplied row 1 by 3 and row 3 by 1/2, we get exactly this matrix. And so next what we want to do is replace row 1 with row 1 minus row 2 so that we can have a 0 where this top 6 is. So then we have 3, 0. 12 minus 60 is 72. 27 minus 126 is 153. Okay, so next let's multiply row 2 by 1/6 of row 2. So 0, 1, minus 10, and minus 21. So 6 times 21 is 126. And then we'll just copy down row 3. Okay, now I really want to have a 7 here so that I can have a 0 where this 7 is. So let's multiply row 2 by 7. And let's multiply row 1 by 1/3. Okay, so next we can replace row 3 with row 3 minus row 2. So we can get a 0 here. So 0, 7 minus 7 is 0. 9 minus 70 is 79. 11 minus 147 is 158. Okay, so this should be our third row. And then in row 2, we want to multiply by 1/7, and that's just to return it to this state. And then we'll just copy down row 1 as is. Okay, so now our second goal is complete. We have zeros above and below our second pivot. Now we can see that 2 times 79 is 158, so we can divide or multiply throughout in row 3 by 1/79th. So we will get 1, 2 there. But we can also multiply by the appropriate number so that we can clear that minus 10. So in row 3, we'll replace row 3 with 10 over 79 times row 3. So 0, 0, 10, 20. Okay, next we want to replace row 2 with row 2 plus row 3. So 0, 1, 0, minus 1. Now, in preparation to deal with this 24 here, let's multiply row 3 by 24 over 10. So we have 0, 0, 24, and 48. And we'll leave row 1 alone for now. So replacing row 1 now with row 1 minus row 3, we have 1, 0, 0. 51 minus 48 is 3. We'll leave row 2 alone and multiply row 3 by 1/24th of row 3. So we have 0, 0, 1, and 2. And now this is done. This is the row reduced echelon form of the original augmented matrix that we found. So this gives us alpha is 3, beta is minus 1, and gamma is 2. So going back then to our original question, where we were asked to write V as a linear combination of U1, U2, and U3, we now have that. We have 3U1 minus U2 plus 2U3 is supposed to be equal to V. But let's check. So 3U1 is 369, minus U2 is minus 2, minus 5, 1. 2U3 is 8, minus 4, 6. Okay, and so adding these together, 3 minus 2 is 1, 1 plus 8 is 9, 6 minus 5 is 1, 1 minus 4 is minus 3. 9 plus 1 plus 6 is 16. And so, yes, this is V. So we've expressed V as a linear combination of U1, U2, U3, and this is the exact linear combination. Okay, question 2. Consider the following vectors in 3 space. So uppercase V is the vector space, which is 3 space. And so we are asked to show that span U1, U2, U3 is equal to 3 space. So let's talk first about the strategy here. What is span of U1, U2, U3? Well, this is the set of all linear combinations of U1, U2, U3. So the set of all alpha U1 plus beta U2 plus gamma U3 is such that alpha, beta, and gamma are real numbers. Is an element of the set of real numbers. And this is what the span of U1, U2, U3 is. Okay, so our strategy is we show that span U1, U2, U3 is a subset or equal to R3, and R3 is a subset or equal to the span of U1, U2, U3. Okay, so let's begin with the first part, which is the easy part. So to show that span of U1, U2, U3 is a subset or equal to R3 if lowercase v is an element of span of U1, U2, U3, then v is of the form alpha U1 plus beta U2 plus gamma U3, where alpha, beta, gamma are real numbers. And this is clearly an element of 3 space, so this is actually trivial. Okay, now conversely, to show that R3 is a subset or equal to the span of U1, U2, U3, what we do is we take an arbitrary vector in 3 space, say W equal to PQR in 3 space. So we must show that W is also an element of span of U1, U2, U3. In other words, let's rephrase this. So can we always find alpha, beta, gamma in the set of real numbers such that W, PQR, irrespective of what PQ and R are, can we always find alpha, beta, gamma such that this is alpha U1 plus beta U2 plus gamma U3. Okay, let's rephrase this again. So can we always solve for alpha, beta, gamma such that taking these numbers from U1, U2, U3, okay, so can we always solve this matrix equation for alpha, beta, gamma, which is the concatenation of U1, U2, U3 here. And then if you actually multiply this out, this is what you get right here. So can you always solve this equation? All right. And so we can always solve this equation whenever this matrix here on the left is invertible. So is this matrix invertible? Okay, and so we can do that by calculating its determinant. So the determinant of this matrix is 1 times the determinant 2, 5, 3, 8 minus 1 times the determinant 1, 5, 1, 8 plus 1 times the determinant 1, 2, 1, 3. Okay, so simplifying this, we have 2 times 8 is 16, so 16 minus 15 for 3 times 5, and then minus, in brackets, 8 minus 5, and then plus, in brackets, 3 minus 2. Okay, and so simplifying, we have 1 minus 3 plus 1, which is minus 1, and this is non-zero. So the fact that this is non-zero shows that this matrix here is invertible. So this inverse exists. And so it follows then that alpha, beta, gamma, if we call this matrix here uppercase A, so alpha, beta, gamma, the vector is A inverse times the vector PQR. And it doesn't matter what PQ and R are as real numbers, because irrespective of what they are, A inverse exists, and we can always find a corresponding alpha, beta, gamma. So it's like this. If your friend gives you a PQ and R, you can always find alpha, beta, gamma such that you can solve this equation right here. And hence, for that vector W that your friend has found, you can always find the corresponding alpha, beta, gamma that puts that W in the span of U1, U2, U3. So you can always find that W that they have given you as a linear combination of U1, U2, U3. And so we see then that if we take an arbitrary element of R3, it's in the span of U1, U2, U3, because it's a linear combination of U1, U2, U3. Okay, and so what we've done, we've shown span of U1, U2, U3 is a subset or equal to R3, and R3 is a subset or equal to span U1, U2, U3. Okay, and so since we've shown that each is a subset of the other, the two sets have to be equal. So the sets, R3 and span of U1, U2, U3 are equal. And since they're both vector spaces, the vector spaces are equal. Okay, and so we're done with question 2. Question 3. Show that span of U1, U2, U3, U4 is not equal to R4. Are the vectors U1, U2, U3, U4 linearly dependent or linearly independent? So what we want to do here is form the matrix A, which is the concatenation of U1, U2, U3, U4. And so this is 1, 0, 3, 4 in the first column, 2, 1, 0, 8 in the second column, 1, 1, 1, 0 in the third column, 2, minus 1, 0, 20 in the fourth column. And so we want to row reduce this, finding the row reduced echelon form of this, then seek out where the pivots are and find the corresponding vectors u1 through 4 so that we can see a reduced spanning set for the vectors u1 through u4. Okay, so let's row reduce this. Now the GCD of 1, 3, and 4 is 12. So I want these numbers to be 12. So let's multiply the first row by 12. Let's leave the second row as is. Let's multiply the third row by 4. Let's multiply row 4 by 3. Okay, and so now we want to have zeros where these two 12s are. Okay, so we're replacing row 3 with row 1 minus row 3. So we can get a 0 where this 12 is. Well, 24 minus 0 is 24. 12 minus 4 is 8. 24 minus 0 is 24. Now we want to replace row 4 with row 1 minus row 4. So 12 minus 12 is 0. 24 minus 24 is 0. 12 minus 0 is 12. 24 minus 60 is minus 36. Let's leave row 2 as is. But actually, no, let's multiply that by 2. So 0, 2, 2, minus 2. Let's multiply row 1 by 1/12 of row 1. So we have 1, 2, 1, 2. And now you can see why I have multiplied row 2 by 2 so that these two match. And in this next step, I can replace row 1 with row 1 minus row 2. And it gives 0 there because we want this to be our second pivot here. Okay, so let's do that, replacing row 1 with row 1 minus row 2. We have 1, 0, minus 1, and 4. Okay, now let's replace row 3 with 1/8 of row 3. So we have 0, 24 over 8 is 3, 1, and 3. Let's replace row 4 with 1/12 of row 4. So 0, 0, 1, and minus 3. Now let's replace row 2. Because we have a 3 there, let's replace row 2 with 3 over 2, row 2. So we'll have 0, 3, 3 minus 3. Okay, great. We want this to be our pivot here. So we now want to replace row 3 with row 2 minus row 3. So 0, 0, 2, minus 6. Let's multiply row 2 by 1/3. 0, 1, 1, minus 1. And we'll keep row 1 the same. Okay, now you can clearly see that row 3 and row 4, they are multiples of one another. So in our next step, let's replace row 3 with 1/2 of row 3, which is row 4. And so we are going to get a row of zeros in row 4 because this will be row 3 minus 2, row 4, which gives us a row of zeros there. Okay, so we have a row of zeros. Now, this means that this 1 here will be our third pivot. We want zeros above it. And so continuing, we'll replace row 1 with row 1 plus row 3. So that's 1, 0, 0, 1. Let's replace row 2 with row 2 minus row 3. So 0, 1, 0, 1 minus 3 is 3 minus 1, which is 2. And then we'll copy down row 3 the same and copy down row 4 the same. Okay, so this is in row reduced echelon form. And I'll abbreviate that RREF. We have our pivots are 1s. We have zeros above and below the pivots. Let's identify where the pivots are. So this says look at columns 1, 2, and 3 of the original matrix A, extract those 3 vectors. And so what we can learn then is that span of U1, U2, U3, U4 is equal to span of U1, U2, U3. Okay, and because there are only 3 vectors, this cannot be all of 4 space. So this is not equal to 4 space. It also tells us that, we come back to the question, it also tells us that the 4 vectors U1, U2, U3, U4 are linearly dependent. They depend on each other. So there are scalars such that the alpha times u1 plus beta times u2 plus gamma times u3 plus delta times u4 is equal to 0, the 0 vector, where alpha, beta, gamma, and delta are not all 0. Okay, and now to finish this, let's see. So I'll just rewrite these vectors. This is u1, u2, u3, and u4. Can we find coefficients here such that the sum gives us 0? And that clearly shows us that these vectors would be linearly dependent. We already know this from the calculations we've done, but let's just make it crystal clear. So because we have a 0 there and a 0 there, I'm going to choose a -3 in front of this and a 1 in front of this. Okay, so that we get 3 minus 3 is 0. I'm going to solve it like this and then take it over to the other side. Okay, and so next, if that's the case, what do I want to do here to get a 20? So 4 plus 16, so let's go 2 times this. Okay, so 4 plus 16 is 20. Does this work elsewhere? 3 plus 0 minus 3 is 0. Yes. 0 plus 2 minus 3 is -1. Yes. 1 plus 4 minus 3 is 2. Okay, yes, that's true. So we have found that this fourth vector is a linear combination of the first three. This also confirms what we've learned in our previous calculations, but it tells us that 1 times u1 plus 2 times u2 minus 3 times u3 minus u4 is the 0 vector, but these coefficients are not all 0. And so the vectors u1, u2, u3, and u4 are linearly dependent. So, okay, question 4. Suppose that the vectors u, v, and w are linearly independent. Show that the vectors u plus v, u minus v, u minus 2v plus w are also linearly independent. Let's here give the definition of linearly independent. So if whenever alpha u plus beta v plus gamma w is the 0 vector, we must have alpha, beta, and gamma equal to the 0 scalars. Okay, so this is what we're going to assume here. So we'll begin by saying assume u, v, and w are linearly independent. And I like to abbreviate that LI sometime. Okay, so now consider a times u plus v plus b times u minus v plus c times u minus 2v plus w equals the 0 vector. Are we forced to have a, b, and c all 0? So let's find out. So expanding, we have au plus av plus bu minus bv plus cu minus 2cv plus cw is the 0 vector. Okay, now let's collect in terms of u, v, and w. So we have a times u plus b times u, so a plus b plus c times u. And then coefficients of v, we have a times v, we have minus 2c times v, and then the coefficients of w is just c times w. Okay, so we have this. Next, since u, v, and w are linearly independent, we must have a plus b plus c equals 0. We must have a minus 2c equal to 0. And we must have c equal to 0. All right, so here's our alpha, beta, and our gamma. Okay, so now let's solve this system of simultaneous equations for a, b, and c. So clearly we have c is 0 from the bottom line. So that tells us that a has to be 0. And if both a and c are 0, then b is 0 as well. And of course, c is 0. Okay, so we know now that a, b, and c are 0 if we have this equation, assuming that u, v, and w are linearly independent. So what does this tell us? Well, it tells us then that u plus v, u minus v, u minus 2v plus w have to be linearly independent as well because their coefficients are forced to be all 0. So hence, u plus v, u minus 2v plus w are linearly independent. Okay. Question 5. Show that the vector space V, being the vector space consisting of polynomials with real coefficients, cannot be spanned by a finite number of such polynomials. Okay, so suppose this is span of f1, f2, etc. up to fn, where n is some positive integer. Okay, so this is a finite number. There are n of them in our assumption. We want to show that this assumption leads to a contradiction. Now, since each of these polynomials in our proposed spanning set has finite degree, let the degree of fj be equal to dj. Okay, now let m be equal to the maximum of all the degrees. Okay, and so what we want to do is form a polynomial that cannot be spanned by these because the polynomial has a degree greater than the degree of each of these. So let's let g of t be equal to 1 plus t to the power of m plus 1. So clearly g of t is not a linear combination of f1, f2, etc. up to fn, because the degree of g of t is greater than that of each of f1, f2, etc. up to fn. And so this is a contradiction to this assumption. So that original assumption must be false, and so the polynomials with real coefficients cannot be spanned by a finite number of polynomials, which completes the question. Okay, question 6. Consider the vectors u being 1, 2, 3, and v being the vector 2, 3, 1 in 3 space over the real numbers. So the first part 1, asks us to write w as a linear combination of u and v. So w is the vector 1, 3, 8, and we seek to represent 1, 3, 8 as alpha u plus beta v. And we're seeking the alpha and the beta there. Okay, so let's expand on the right. So we have alpha plus 2 beta, then we have 2 alpha plus 3 beta, then we have 3 alpha plus beta equal to 1, 3, 8. Now this gives us 3 scalar equations. Alpha plus 2 beta is 1, 2 alpha plus 3 beta is 3, 3 alpha plus beta is 8. So are these consistent? Can we solve for alpha and beta? Okay, let's take our third equation and multiply that by 2, like so. And now let's subtract these equations. So 6 alpha minus alpha is 5 alpha. 2 beta minus 2 beta is 0. 16 minus 1 is 15. And so we see that alpha has to be equal to 15 over 5, which is 3. And so if alpha is 3, then beta is 8 minus 3 times 3, and so that's minus 1. Now we have just used equations 1 and 3 here. We have not used equation 2. So let's take the two of these numbers, sub them into equation 2. 2 times 3 plus 3 times minus 1 is 6 minus 3, which is 3. That is consistent with this. And so we have a consistent solution, which says that 3u minus v is equal to w. Okay, let's move on to part 2 of question 6, where w is 2, 4, 5. And so again, we seek alpha and beta such that alpha times 1, 2, 3 plus beta times 2, 3, 1 is equal to 2, 4, 5. Okay, so expanding, we have alpha plus 2 beta must be equal to 2. 2 alpha plus 3 beta must be equal to 4. 3 alpha plus beta must be equal to 5. Okay, so let's try the same thing. Multiply the third equation by 2. And then let's subtract third equation minus the first equation so that the 2 betas vanish. So we have 5 alpha is equal to 8. So alpha is 8 over 5. Okay, and then using this third equation, beta is 5 minus 3 alpha, which gives 25 minus 24 all over 5. So beta is 1/5. Okay, so given those two, is this consistent with the second equation? 2 times 8/5 plus 3 times 1/5 is equal to 16 plus 3 all over 5, which is 19 over 5. This is not equal to 4. So we see then that the system of equations is not consistent, and so there are no real numbers alpha and beta such that the linear combination of U and V gives W. Question 6, part 3. So we have alpha U plus beta V is equal to the vector 1, K, 4, and we are asked to find a real number K such that this is consistent. So the question says, find K such that W is a linear combination of U and V. Okay, so the question here is, for what value of K is this system consistent? So alpha times U is alpha, 2 alpha, 3 alpha. Then beta times V, 2 beta, 3 beta, beta. This is supposed to be equal to the vector 1k4. Okay, again, this gives rise to 3 scalar equations. Alpha plus 2 beta equal to 1. 2 alpha plus 3 beta equal to k. 3 alpha plus beta is equal to 4. So let's try the same things that we did before. Let's multiply the third equation by 2. Okay, subtracting equation 3 minus equation 1, we've got 5. This should be alpha here. 5 alpha is equal to 8 minus 1, 7. And so alpha is 7 over 5. Okay, then substituting that 7 over 5 back into the third equation, we have beta is 4 minus 3 alpha. That should say alpha. Okay, now simplifying this, we have 20 over 5 for 4. So 20 minus 21, which is 3 times 7, all over 5. So this is minus 1/5. Okay, now what is the value of K such that this system is consistent? So 2 alpha plus 3 beta is equal to 2 times 7/5 plus 3 times minus 1/5. So we have 14 minus 3 is 11 over 5. And so K must be equal to 11 over 5 for this system to be consistent, and hence the vector W to be a linear combination of U and V. Okay, part 4, find conditions on ABC such that ABC is a linear combination of U and V. So alpha 1, 2, 3 plus beta 2, 3, 1 is equal to ABC. Okay, again, this gives 3 scalar equations. Alpha plus 2 beta equal to A, 2 alpha plus 3 beta equal to B, 3 alpha plus beta is equal to C. Multiplying the third equation by 2 again, and subtracting, we have this system of equations. So 2 beta minus 2 beta is 0. So we have 5 alpha equal to 2C minus A. And so this tells us that alpha is 2C minus A all over 5. So using that in our first equation gives us beta is C minus 3 alpha, like so. Now simplifying this, we have 5C minus 6C plus 3A all over 5. And so beta is 3A minus C over 5. Okay, so we now have alpha and beta. So again, the question is this consistent? So if it is consistent, then we have 2 times alpha 2C minus A over 5 plus 3 times beta 3A minus C over 5. This is supposed to be equal to B when the vector W is a linear combination of U and V. Okay, so we can simplify this condition somewhat. So we have 4C minus 2A plus 9A minus 3C equal to 5B, and that is 7A minus 5B plus C equals 0. Okay, so for ABC satisfying this, W is a linear combination of U and V. Okay, question 7. Determine whether the polynomials U, V, and W are linearly dependent or linearly independent. So let's let U be equal to the vector 1 minus 4, 3, 3. So you can see I'm just reading off the coefficients. Let V be the vector 1, 2, 4, minus 1. And let's let W be the vector 2, minus 1, minus 3, 5. Okay, so let's form a matrix out of the rows of these. So let's let A be equal to U concatenated with V concatenated with W in placed as rows. 1, minus 4, 3, 3. 1, 2, 4, minus 1, 2, minus 1, minus 3, 5. Okay, now let's row reduce this, seeking the row reduced echelon form of this matrix, but I'm going to do this in Mathematica. Okay, so here you can see I have entered this matrix A, and then around that I wrote row reduce, and then to display that as a matrix, / matrix form. Let's run this. Okay, and so we have the identity on the left and some non-zero numbers on the right. So this tells me that the span of u, v, and w is the span of these vectors that you see in the row, like so. And so we do not have a row of zeros in our row reduced echelon form here. So these vectors u, v, and w are linearly independent. Okay. Question 8, consider the following three subspaces of R3 or 3 space, U1 spanned by the vectors 1, 1, minus 1, 2, 3, minus 1, 3, 1, minus 5. So which of the following U1, U2, U3 vector spaces are equal? So to solve this problem, what we want to do is seek a reduced spanning set for each of these. So let's let A1 be equal to the matrix. And I will just take those vectors and place them as rows of a 3 by 3 matrix. So 1, 1, minus 1, 2, 3, minus 1, 3, 1, minus 5, A2, 1, minus 1, minus 3, 3, minus 2, minus 8, 2, 1, minus 3, A3 equal to 1, 1, 1, 1, minus 1, 3, 3, minus 1, 7. Okay, now A1, row reducing this, let's multiply so that we have 6 in the first column. So 6, 6, minus 6, then 6, 9, minus 3, then 6, 2, minus 10. Okay, replacing row 2 with row 2 minus row 1, we have 0, 3, 3. Replacing row 3 with row 1 minus row 3, we have 0, 4, and 4. And then replacing row 1 with 1/6 of row 1, we have 1, 1, minus 1. Okay, now replacing row 3 with a quarter row 3 minus a third row 2 gives a row of zeros, and you can see that these are parallel rows. Replacing row 2 with 1/3 of row 2, we have 0, 1, 1 there, and then let's keep the top row the same for now. Okay, next, replacing row 1 with row 1 minus row 2, we have 1, 0, minus 2, 0, 1, 1, and 0, 0, 0. Now this is in row reduced echelon form. Let's do the same thing for A2. Again, we can place a 6 in the first column by multiplying by the appropriate numbers in each row. 6 minus 18, 6 minus 4 minus 16, 6, 3 minus 9. Okay, replacing row 2 with row 2 minus row 3, we have 0, 2, 2. Replacing row 3 with row 3 minus row 1, we have 0, 9, and 9. Replacing row 1 with 1/6 row 1, we have 1, minus 1, minus 3. Okay, so again, we get a row of zeros in the third row. Multiply row 2 by 1/2, and then replacing row 1 with row 1 plus row 2. Okay, and so we see that these two have the same row reduced echelon form, and so this shows us that the span of the vectors in the rows of A1, span of these three vectors is equal to the span of these three vectors. So let's write that. This shows that span equals the span, the vectors in the spanning set for U2, which is equal to the span of the two vectors 1, 0, minus 2, and 0, 1, 1. And so we see then that U1 is equal to U2. Okay, now what about U3? So A3, looking at this, multiplying row 1 by 3, row 2 by 3, and now replacing row 2 with the difference row 1 minus row 2, replacing row 3 with row 1 minus row 3, replacing row 1 with 1/3 of row 1. We now have this, and then finally replacing row 1 with row 1 minus row 2, we have 1, 0, 2, 0, 1, minus 1, 0, 0, 0. And so this is not the same row reduced echelon form as we have here. It looks very similar, but it's different. And so this tells us then that U3 is not equal to U1 nor U2.